Even though a proton transfer reaction can be written for any combination of acid and base, not every reaction will occur. And what that means is not every proton transfer reaction will favor products. To better understand why some proton transfer reactions favor products and others don't, let's look at this generic proton transfer reaction right here shown in equation 6.4. The reactant acid, which is shown as HA here, can donate a proton to the base, which is just shown. This is a generic base, the base with the electrons here, to form the products. But because of equilibrium, right, which you remember from general chemistry, the reverse reaction is also possible. And remember, we have a bidirectional arrow here that shows us that. And so what can happen is the conjugate acid here can donate its proton to a base to form reactants, right, and go back this way. So we view these two acids, this acid and this acid, as being in competition with each other. And the stronger acid will win and donate its proton. So we kind of view it this way, like it's like a big competition. This acid is pushing the reaction this way, and this acid is pushing the reaction this way, and the stronger acid wins. So if the reactant acid is stronger, then the reaction will tend to result in more products than the reactants, and we say the product side will be favored. If the product acid is stronger, then the reaction will tend to result in more reactants than products, and we say the reactant side is favored. And so maybe the burning question in your heart is, well, how do we know which of the two are stronger? And I'm so glad you asked, because we can use Pka values to help us determine which acid is stronger. So to know which acid is stronger, as I mentioned, we're going to turn to Pka values. And these are experimentally determined values of an acid. So in section 6.3, which is kind of the next section we're going to do, the screencast is just for section 6.2, we are going to discuss Pka values really in depth, including exactly where we get them from, but that is a chemical equilibrium, if you remember from general chemistry. For now, we want to remember a few features, which I have bullet pointed here for you. A lower Pka value, which is less positive or more negative, represents a stronger acid. So strong acids have low Pka values. And then each difference of 1 in a Pka value represents a factor of 10 difference in acid strength. This is because it's a negative log value. And so because it's on a log scale, that's where we get the 1 to 10. Now, with all of this in mind, you need to familiarize yourself with table 6.1, which has lots of Pka values of several representative acids in order of decreasing acid strength. And then we have a more complete table of Pka values in Appendix A. I'm gonna photocopy table 6.1 and give it to you in class. And of course, you would be given a table like that, or there are certain Pka values on a test, but we are also going to learn how to predict Pka values when they're not known. Now, the strongest of these acids, which would have a Pka of about -13 on this table, if you're looking at this table, appears at the very top of the first column, and the weakest of those acids, if you're looking at this table, appears at the bottom of the second column. Notice, and I have these here. So at the very top here, we have ethane, where the Pka is 50, and then trifluoromethane has a Pka of negative 13. So when you look at table 6, that's a large range there. So it's 10 to the negative 50th to 10 to the 13th. But we're just looking at these pKa values here. If you want to compare two pKa values, what you would do is you would take negative 13 and subtract 50. There's a 63 difference there. And that means that the trifluoromethane sulfonic acid is 10 to the 63rd times stronger in acid than the ethane. So we can use the difference in pKa values here to tell us how much stronger one acid is than another. I cannot flip with this program to show you table 6.1 and continue to talk. It will cut me off and jump around. But if you're looking at table 6.1, and again, you will see that I'll hand it out in class. That's one of the things to be aware of. So having a pKa value at our disposal really is very helpful for us. And so I want us now to look at two proton transfer reactions. And these are shown in equation 6.5 and 6.6. So these are two separate reactions. And so I want you to notice, so let's look here in equation 6.5, the stronger acid is on the reactant side. So we play a comparisons game a lot in organic chemistry. And so if we look here, HCl here has a pKa of negative 7. And water, which is the acid here, has a pKa of 14, okay? And so we identify what's the acid based on the Bronsted-Lowry definition, and so that's the conjugate acid. And so when we look at this, we see that negative 7 is a lower pKa value than 14, and so the equilibrium favors the side opposite the strong acid. So it's kind of like this is the strong acid, and it's really, really strong, and it's going to push this way. And so we would say that this is product favored. If you look at equation 6.6, this is the acid here with a pKa of 36, and then we still have water here with a pKa of 14. Well, 14 is less than 36, and so 14 is going to be the stronger acid, and it's going to push that way, and the equilibrium is going to favor this side here. Now, we can also calculate how much it's going to favor, right? So the pKa value, the difference between, if we take the difference between negative 7, right, and 14, and we're really looking for just the absolute value here. So negative 7 minus 14, there's the difference, and that difference would be 21, right? Absolute value, so we'll drop that negative. And so we take it for a 10 to the 21st. The reactant acid is 10 to the 21st times stronger, and so then the product acid, right? So HCl is 10 to the 21st times stronger than water, and so the extent to which the product is favored is 10 to the 21st. So that's the extent to which the product is favored. Then when we look here, the difference between, and again, this is absolute value, the difference between 36 and 14 is 22. And so we can say the extent to which the reactant is favored is 10 to the 22. So that's the extent to which the reactant is favored. So what the pKa does for us is not just tell us which side of the reaction is favored, but it can also tell us by how much. So let's do an example. Okay, it says predict which side of the reaction is favored and to what extent is that side favored. And I left out the reaction. So let me supply you with the reaction here. It is H3C. I don't know where it went. OH plus H2N, CH3 goes to H3C, C double bond O, O minus plus H, NH2 plus CH3. All right. And so I'm going to show the mechanism here. When I'm showing the mechanism, I can evaluate what's happening. So I see that we lose a hydrogen here versus here. So do you remember those things as a kid where you would be shown two pictures and you have to pick the things that are different? This is kind of that same thing. So I see that I've lost this hydrogen from this molecule to this molecule, and I've gained a hydrogen from here to here. So I can come up and I can predict that mechanism where I can say, hey, look, these electrons are going to go steal that hydrogen. Those electrons are going to go back on that oxygen. And now I've got my product there. When I do this, I can identify what the acids are. So if we look here, the CH3, C double bond O, OH, that is an acid because it's donating its proton. So that means that's a base. And so then I can identify this is the conjugate base, and then this as the conjugate acid. So now when I'm trying to predict which side of the reaction is favored and to which extent that's favored, I've already kind of done number one, which is to identify the acid on the reactant side and the product side. So I've done that. I've identified those on the products. Then I need to ask myself, which one is stronger? And so you need to compare Pka values. And you can either use Appendix A or Table 6.1, okay? And so I'm going to come here and I'm going to say, okay, I'm trying to evaluate this molecule. And so when we look at the Table 6, when we look at this molecule, it's CH3CO2H, and it has a pKa of 4.75. And then over here, the conjugate acid, when we look at the table, you should find that this pKa is 10.63. And so we've identified the two pKa values. And then it says, which is the favored side of a proton transfer reaction? The side that has the stronger acid or the opposite, or the side opposite the stronger acid? So that's kind of a weird way to do it, right? And so when I look at this, I say, okay, hey, look, 4.75 is a lot lower than 10.63. So that means this is the stronger acid. And so it is going to push the reaction that way. And so what we know from this is that the product side is favored. And then we're going to answer the second question. To what extent is that side favored? Well, so 10.63 minus 4.75 is 5.88, right? And so when we look at this, the reactant side is favored 10 raised to the 5.88 times, right? Or if we wanted to solve that out, it would be 7.6 times 10 to the fifth. So that's how much the reactant side is favored, which is a very, very large amount. So this is how we can use pKa's to predict which way the reaction is favored, and then, of course, by how much. Now, we've completely been talking about acid strengths, and pKa values represent acid strengths, but we can also use them to determine the strength of bases when we're making comparisons. The stronger base is the one with the weaker conjugate acid, okay? The weaker base is the one with the stronger conjugate acid. So, strong base, weak conjugate acid. Weak base, strong conjugate acid. This, for me, is really hard. It just is, because it's an inverse relationship. And so there's an inverse relationship between the strength of an acid and the strength of its conjugate base. And this arises because the acid and its conjugate base are found on opposite sides of the proton transfer reaction. So I like to do an example, okay, to kind of help with this. And so it says, which base is stronger, H minus or HC triple bond C minus? Okay. Well, we only have pKa values, and those help us evaluate the acids. So we first need to write the conjugate acid. So your first step here is first write the conjugate acid by adding an H plus to the base. And the bases are given here for you. And so what that means is H minus is going to become, we add an H plus, it's going to become H2. And HC123, C minus, is going to become HC123CH. All we've done is add a proton. What we have done now is we have said, hey, look, this is the acid, and this is its conjugate base. And then over here, this is the acid, and this is its conjugate base. Remember, these can only differ from each other by a proton. So I look up the pKa of the acid, and when I go to the table, I find H2, and the pKa equals 35. And then I find the pKa of HC, triple bond CH, and that's 25, okay? And so when we look at this, remember, this is a comparison. HC, triple bond CH, because its pKa is lower, it's going to be the stronger acid, right? So that's the stronger acid, and so that means that is the weaker base, okay? This is the weaker acid of the two because it has a higher pKa, and so that means this is the stronger base. So the stronger base of the two is the H minus, but we have to view it from the acid. And I'll be really, really honest. If I don't follow these steps and write it out like this, I will confuse myself. So my suggestion is please, please, please write those out. Now, knowing which side of a proton transfer reaction is favored helps us understand an important phenomenon called the leveling effect. Now, so let's talk about the leveling effect. Let's say we want to carry out a reaction, and reactions sometimes will happen just by themselves, but most often we need a solvent. So when we do a reaction, we have some sort of solvent. We've used water as a solvent a lot. But we don't want the solvent to react to whatever our species that we add are, to our reactants. Because there's a couple things why we don't want this to happen. One is we'll get side products that we eventually have to separate out, and that's pain. And then two, we could use up those really expensive reactants in all these side reactions, and we don't want that to happen either. So, when a reactant is too strong of an acid or base, it can react with a solvent in an undesired proton transfer reaction. And again, this is a side reaction. It's a pain and it's expensive. We don't want that to happen. And so what happens is the reactant doesn't remain intact to undergo the desired reaction. And so that undesired proton reaction is called the leveling effect. Kind of like if in construction you go and just level something and it's no longer there. The reason this is the way I like to remember this is if this occurs, you've leveled your reactant and it's no longer there, right? And so here is kind of the summary of this. The strongest acid that can exist in solution to any appreciable concentration is the protonated solvent. And then the strongest base that can exist in solution is the deprotonated solvent. And I want to show you an example because this is really hard to grasp, I feel like, without an example. So I want us to look at the leveling effect in water. So we look here, and in water, right, H3O plus is the protonated water, is the strongest acid that can exist, and then OH minus, which is deprotonated water, is the strongest base that it can exist. And so, and to see why this is, I want us to look at what would happen if an acid stronger than H3O plus or a base stronger than OH minus were placed in water. So HCl here is a stronger acid than H3O plus, okay? And so what that means then is HCl could donate its proton to water according to the proton transfer reaction in 6-7. And so because HCl is significantly stronger than H3O plus, HCl is going to win that competition, and the product side is going to be heavily favored. So this is what you're going to have in solution. That means that when HCl is added to the water, this reaction would take place until HCl was all gone, and you would only have H3O plus. So if you wanted HCl to react with something else, it's going to be all used up by your water. It'll be completely gone. And that's a problem, right? So something similar happens when you use a base that's stronger than OH minus, like this little guy here. So CH32N minus, it's a base. It's going to remove a proton from water. And what you find here is that the product side is really heavily favored here because the acid on the reactant side, that water, is a stronger acid than the one on the product side. So when this is added to water, it's completely consumed, leaving OH minus as the base. And so you don't have any more of this left. And so it can't react with something else. So basically water has come in and leveled your reactants in both of these cases. So the important lesson to take away from these examples is that if we want to carry out a reaction involving either HCl or CH3 2N- as a reactant, then water is a poor choice of solvent because each of these species is going to be consumed in an undesired proton transfer with water, right? We don't want these things to happen. And so we would say that with respect to the leveling effect, water is an unsuitable solvent for either HCl or CH3N-, right? And so we can make some generalizations then. A solvent's unsuitable for a particular reactant are if R is a stronger acid than the solvent's conjugate acid. Another way of saying this is that that reactant has a lower pKa, and then R is a stronger base than the solvent's conjugate base. And another way of saying that is the conjugate acid of R has a higher pKa than the solvent. Okay, so there's just kind of a summary here of what makes that unsuitable. So let's do an example. Okay, CH3 is a strong base. Verify that diethyl ether, which is shown here, is a suitable solvent for CH3 according to the leveling effect. So here are the questions that we need to ask ourselves. Is CH3 a stronger base than the conjugate base of CH3CH2 diethyl ether, CH3CH2O CH2CH3? So for CH3 to be a stronger base than diethyl ether's base, and diethyl ether's base here would be CH3CH2O CH minus CH3. We're going to remove one of the protons. It's more likely to remove a proton next to the oxygen. We're going to worry about why that is later. Just trust me on this, that this would be the base. Okay. So for CH3 to be a stronger base than this, CH3 must be a weaker acid than than diethyl ether. So CH3 must be a weaker acid than CH3CH2O CH2CH3. Okay, so instead, what we find is that the pKa of CH3 is 38, right? And that's lower than the pKa of CH3CH2O CH2CH3, which is 45. So we're comparing the pKa's here. And so when we look at this, it says, will an undesired proton transfer reaction occur between CH3 and diethyl ether? And so the question here is, if you have CH3 will it react with diethyl ether to form right? And so based on kind of what we were looking at before, if this pKa is 45 and over here this pKa is 38, then the reaction, this is the lower pKa, and so what we're going to see here, our reactants are favored, and they're favored by a lot, right? So 45 minus 38. My math is right, that's 7, so that'd be 10 to the 7th, okay? So what this means for us is, hey, look, we want to use this as a solvent. We don't want there to be any sort of proton transfer reaction. We need this to stay over here and these two guys not react. And this is perfect for us because this pKa is much higher than this pKa over here. And so that means this is the stronger acid. It pushes that equilibrium this way. And so these two guys won't react. And that means this guy here is free to react with whatever else you put in the reaction. Okay? And so this diethyl ether is a suitable solvent. So this is a good, diethyl ether is a good solvent for this reaction. Now, in section 6.2, earlier, we saw that if an acid or base is too strong, then it cannot exist in a solution at any particular concentration. In many cases, however, both an acid and its conjugate base can exist in a solution in substantial concentrations, think like weak acid-base pairs, when neither the acid nor the conjugate base is really strong, so those weak acid-base pairs. And when this happens, the acid and conjugate base exist in solution together when they're in equilibrium with each other. And I want us to remember from general chemistry, equilibrium is when the rate of the reaction in the forward direction equals the rate of reaction in the reverse direction. Okay. Now, what this means is that the concentration of reactants and products don't change. It doesn't mean they're equal to each other. It just means the concentrations of reactants and products don't change. So here is an example of a weak acid-base pair. We have ethanoic acid here. This is also known as acetic acid or vinegar, and this is its conjugate base. It's an ethanoate anion, which is also called an acetate anion. And so both of these are present in solution because it's a weak acid-base pair. Now, when an acid and its conjugate base are equilibrium with each other, their relative concentrations can be controlled by a change in concentration of any of the reactants or products because of Le Chatelier's principle. So I want you to remember Le Chatelier's principle from general chemistry. It just states if a reaction is at equilibrium and the reaction experiences a change in reaction conditions, right? And we talked about a lot of those: concentration, temperature, pressure, volume, any of that. Then the equilibrium will shift to counteract that change. Okay. Now, specifically, a reaction can be shifted in the forward direction by the addition of reactants or removal of products, and then it can be shifted in the reverse direction by the addition of products or the removal of reactants. Notice in water, if we're in water, then we form H3O plus, and H3O plus is representative of pH. So sometimes, remember, if the pH changes, that changes our concentration of H3O plus. So that opens the gate for me to review pH. I want you to remember the standard unit of concentration is moles per liter, but when we think about H3O plus, it's more convenient to work with units of pH, and pH equals negative log of that H3O plus concentration. Now, the pH of a solution is a measure of the solution's acidity. We all remember that from Gen Chem. And so a lower pH corresponds to a higher concentration of H3O plus. So if we have a lower pH, that means we're increasing our concentration because it's a more acidic solution. So for example, right, if we have a lower pH, we'll increase the concentration of H3O plus here, and it's going to shift equilibrium this way towards the reactants. If we raise the pH of the solution, then it's going to decrease the H3O plus and shift the reaction towards the products. So just a friendly reminder to do watch out for those pHs, because that language, that lower pH, means a higher concentration of H3O plus. Now, the final thing that we cover in 6.2 is something that you're going to use in biochemistry. And basically, acids can have different ionization states. And the dominant ionization state depends on the solution's pH. So basically what we're saying is, look, you can have an acid that's has the proton, or the conjugate base that doesn't. And which state you have present depends on where the equilibrium lies. If the equilibrium lies over here, then that proton's going to be on your acid. If the equilibrium lies here, you're not going to have a proton on your acid. So the protonated acid will be the dominant form when the pH of the solution is lower than the pKa, right? So the pH of the solution is lower than the pKa of the acid, okay? If it's lower, I like to think of that as being more acidic, okay? A minus will be the dominant form when the pH of the solution is higher than the pKa. And I like to think of that as being more basic, right? And then the acid, the HA and the A minus will be present in equal amounts when the pH solution equals the pKa. So I like to do an example. So for example, we are going to look at this guy, CH3 CO2H. Okay, this is our acetic acid. It has a pKa equal to 4.75. Okay, and so I may ask, hey, what's the dominant form when the pH equals 2? So what's that dominant form? So here's what I do. I evaluate and I say, okay, hey, look, the pKa is 4.75, okay? 2 is a lot less than 4.75. That means 2 compared to 4.75 is a heck of a lot more acidic, okay? So 2 is more acidic compared to 4.75. And so that means that more acidic form, the one with the proton, will be present. And so that's CH3CO2H. Well, what's the dominant form then when the pH equals 6? Well, 6 is a lot bigger than 4.75. So 6 is more basic than 4.75. And so it's more basic than the pKa. So that means the basic form, or the conjugate base, will be shown, and that's CH3CO2 minus. All we've done is lost our proton. That's it. All these questions are asking is, which form's going to be here, the conjugate acid or the conjugate base? So this wraps up for us Screencast 2, where we really just focused on a heck of a section, 6.2, looking at pKas. We are going to dig a little deeper into chemical equilibrium and equilibrium constants and Ka values in the next screencast.